In this video, I want to develop a model for the drag force, which is essentially air resistance. So the first thing is for the drag force is to determine that model is really only good under certain conditions, and I'll outline them here. We're going to be looking at low speeds, and by low speeds, I mean anything sort of less than or on the order of 100 meters per second. We're also going to be looking at objects that are small, but still macroscopic. So that's telling us we're looking at sizes that scale from about 5 millimeters to something like 5 meters across. Sort of sets the scale for the types of objects for which this model of air resistance is good. And the other thing is that it's moving through a gas. This model isn't going to be good for more viscous substances like liquids. All right, so given those conditions, we're going to model our drag force magnitude. And so the magnitude of the drag force is going to be given by 1/2 times a constant c, and c is called the drag constant. I'll go through all of these once we see them. Drag constant times rho, that's the Greek letter rho, and rho is the density of the gas that the substance is traveling through, times A. A is the cross section, call it cross-sectional area of the object, and then where this is the speed. And the magnitude is then the speed squared, or v squared. So this is the magnitude of the object, and then it has a direction that's given by the opposite direction of velocity. So the direction of the drag force opposes the velocity. Wherever the velocity vector is, the drag force points in the opposite direction, and its magnitude is given here. So let's look at all of these components of the drag force here. We'll look at the easy ones first. The rho is the density of the gas. And just for example, air density is a 1.2 kilograms per meters cubed at standard temperature and pressure, which is room temperature and 1 atmosphere of pressure. So you can already see the sort of problems that you could have because just the drag force is going to depend on the background density, which depends on the temperature of gas and the pressure, and it can change and all of those things. But if we can assume a standard temperature or pressure, you're looking at an air density of 1.2 kilograms per meters cubed. Of course, v is just the speed. That doesn't need much more consideration. Now this capital C is the drag coefficient. So the drag constant. The drag constant depends on the object, and it depends on everything about the object. Its construction, the material. It depends on the shape, and the entire three-dimensional shape. In fact, if something is designed to be aerodynamic, What they're saying is that they've put a lot of thought and design into making c small as they can for that particular object. Okay. The final one, part of the drag force, is A, which is the cross-sectional area. And I haven't worked with cross-sectional area before. It takes just a couple minutes to get your head around what this means. The cross-sectional area is the area in a plane perpendicular to the velocity. So here, that's my symbol meaning perpendicular, perpendicular to the velocity, covered by the object as it passes through the plane. What does that mean? So imagine a two-dimensional plane, and it's perpendicular to the velocity of the object. That means the object is going to pass through that plane. As it passes through the plane, the area covered by the object is the cross-sectional area. All right, so this is most easily understood by looking at a couple examples. So let me go with a sphere, again, our favorite object, a sphere of some radius r. And let's say it has a velocity v in this direction, and it's going to pass through a plane. Now it's a little, I have to sort of draw this plane in perspective here, but the edge of it is supposed to come directly out of the screen, and so this plane is perpendicular to the sphere. So as it passes through it, it's going to cover an area of the plane that looks like a circle. And that circle is going to have a radius r. And so the cross-sectional area for this object is going to be pi r squared. So let's do a couple more. So if we imagine a cylinder, and this cylinder has length L and radius r, and it also has a velocity here and off to the right, and it's going through this plane that's perpendicular to its velocity. The area covered by the object as it passes through is again going to be an area of a circle. And that circle is going to have radius r, and so the area will be pi r squared. And so the cross-sectional area for a cylinder of radius r, as long as it's going in this direction, is the same as a cross-sectional area for a sphere of radius r. You can also think about it as if what it would look like if the object were coming directly at you. If the velocity is directly towards you, what would you see? And you would see then the edge of the cylinder coming to you, or a sphere. They would both look like a circle of radius r. So for another example here, let's turn the cylinder on its side. So it looks like this, traveling in this direction. And now as it goes through a plane perpendicular to its velocity, what sort of area does it cover? And the area then that it covers is a rectangle. The height of that rectangle we're going to still say this is a cylinder of length L and radius R. And so the area covered by the cylinder then is a rectangle that has, in this case, a height L and a width of 2R. And so the area is equal to 2RL. It's just the length of the bottom, the width of the bottom of the rectangle is the diameter of the circle. And so it's 2RL. You know, another way to think about this, if you want to think about the area covered in a plane by the object passing through it with a velocity, imagine instead, get a different color, where the object is at rest and you have light shining in the direction of the velocity, and the plane is perpendicular to the light. And then that object will cast a shadow on that plane, we'll call it a screen on that plane, that's equal to the cross-sectional area. See again, if I have a cylinder like this, and I have light that's being shown in the direction of the velocity, it then casts a shadow on the screen equal to the cross-sectional area. And just for completion's sake, if we look at our last cylinder, screen, light, and then shadow is equal to the cross-sectional area. And so you can look at it any of these ways, but it's that is the how we determine the cross-sectional area for a three-dimensional object that's traveling with a velocity v. Okay, so let's just do an example. So if I were to put all, but first of all, if I were to put all that together, I would say that the drag force is equal to negative 1/2 this drag constant rho, drag constant c times rho times the cross-sectional area A times the speed squared, and then if v hat is the unit vector of the velocity v, then the drag force is the negative v hat direction. So let's look at a square cylinder that here looks like this. Kind of a poorly drawn square cylinder. We just want a not a cylinder, but a cubic object where it has a base of, say, 2 meters, a height of 1 meters, and a length of 5 meters. So if this object were traveling sort of with a velocity in that direction, the cross-sectional area would then be 1 times 2 is equal to 2 meters. If it were traveling in this direction, then the cross-sectional area would be here. The area would be 5 times 2, or 10. 5 times 1. Of course, this height here is 1, which is 5 square meters. I'm going too fast. 5 times 1, which is 5 square meters. But if it's going up, then that red shaded is the cross-sectional area, and that's 5 times 2, or 10 meters squared. And so that's another way to look at how to determine the cross-sectional area of an object, and it depends if it's not a sphere. It depends on which direction the velocity is going, or which way the object is facing. Now, what I haven't really shown yet is how to come up with the drag constant c. So, as I mentioned, it depends on the object, and it depends how the object is constructed. I will say, however, that c is about 1/2 for spheres, which are our favorite object. And if something else, you either have to be given what the drag constant is, or it's something that you have to calculate. Given that c is about 1/2 for spheres, also note that rho is about 1 for air. And under that approximation, we have a drag force that simplifies to something about -1/4 cross-sectional area times the velocity squared times the unit vector of the velocity. That puts the drag in the opposite direction of the velocity. So if we really want a simple sort of order of magnitude, we can use this even simplified expression. And especially since, c is usually only ever approximately known. Rho varies for conditions throughout the day and where you happen to be near the surface of the Earth. It changes as a function of height and everything else. Oftentimes you may only be getting an order of magnitude estimate for what the drag force is anyway, and you can use this more simplified expression. All right, so for the drag force, remember, even this model only applies under these conditions, sort of low speeds, small but macroscopic objects, and that it's going through a gas. And then you can find these parameters to find the magnitude, and it always opposes the velocity.